Welcome back to the deep dive. If you are a software engineer, a technical leader, or really anyone whose work involves building anything with code right now,
Yep.
the ground beneath your feet isn't just shifting.
It feels like it's dissolving.
It's dissolving and reforming into something entirely new. We're not just talking about integrating a new tool like GitHub Copilot or some internal assistant.
We don't run at all.
The consensus from every major industry roadmap we've analyzed is that the fundamental blueprint, the very job description for what it means to be an engineer, has changed. So we're no longer talking about just surviving this AI wave.
Right.
We are here to provide the essential blueprint for thriving, how you can position yourself as an elite, future-ready engineer.
That's the critical pivot, isn't it? The sheer speed of change. I mean, the fact that a tool that was absolutely cutting edge 6 months ago is now just standard boilerplate.
It's just expected.
It's just expected. And that mandates a strategic, a proactive response. So our core mission today is to really extract the practical strategies, the deep technical skills, and maybe most importantly, the necessary mindset shifts, the ones you need to evolve into what the industry is calling the elite AI native engineer.
And to do that, we've pulled from a lot of sources.
We've synthesized academic research, proprietary engineering roadmaps for 2025 and 2026, and insights from the companies that are really leading this transition. And the numbers, they just reinforce this urgency.
What are we seeing?
Adoption rates for AI coding tools are already sky high. We're generally talking over 80% among developers and even reaching 65% in those really rigorous top-performing firms.
So it's not a niche thing anymore.
It's not. And those who adopt these tools intelligently are seeing tangible productivity gains. I mean, we're talking 20 to 50% velocity improvement right now.
A 50% velocity improvement. That's transformative for any organization. So let's establish the context here for you, the listener. If the job is changing, what exactly is this paradigm shift? What are we moving from and what are we becoming?
The transition is, I think, conceptual. And it's irreversible. The role is moving away from that of a code producer, the person whose primary value was the fast, accurate translation of requirements into syntax.
Just typing the code.
Just typing the code. We are transitioning to an architect of intent and, crucially, a conductor or an orchestrator of sophisticated AI agents.
Okay, architect of intent. Unpack that.
Well, the old paradigm, it demanded mastery of implementation logic. You had to know where to put the loops, how to handle specific API calls. The new paradigm demands the precise definition of the problem, the specifications, and the desired system outcomes, all using structured, clear language that the AI can act upon.
So your job is no longer to write the code, but to design the intelligence that writes the code.
You've got it. That's the core shift.
Okay, so let's dig into that mindset shift first, because when AI assistants first arrived on the scene, the first question everyone asked was, am I going to be replaced?
Of course. It was a natural first reaction.
But the sources we've looked at overwhelmingly suggest a very different consensus among tech leaders now. What is that prevailing sort of post-fear view of AI's role?
The consensus is now absolutely firm, and you see it everywhere. AI will not replace engineers. But engineers who don't use AI effectively will be replaced by those who do. It's that simple. The technology functions as an amplifier. It's an augmentation layer.
Okay, so it makes good engineers great.
It makes good engineers incredibly powerful. Tech leaders are emphasizing that AI excels at handling the repetitive, the mechanical, the boilerplate work, all those tasks that, traditionally consumed maybe 40% of an engineer's day.
Like what specifically? Give us some examples.
Think about generating unit tests, writing API controller scaffolding, translating JSON schemas into type definitions, or even producing basic documentation, all that grunt work.
So by delegating that significant chunk of work, what's the dividend for the engineer? What do you gain back?
You gain back cognitive capacity and time. That's the real currency. And you can then reinvest that into higher order creativity. The elite engineer is freed up to focus on the things AI still struggles with, and struggles with deeply.
Yes, sir.
Complex system architecture, long-term strategic planning, nuanced multi-component problem solving, and vitally interacting with the business stakeholders.
The human stuff.
The human stuff, the messy stuff. You have to view AI as an extremely powerful, tireless junior partner, but one that critically still requires senior-level guidance, critique, and verification.
That reframes the whole value equation, doesn't it? If the AI is handling the typing and the basic implementation, Where should the human engineer really focus their cognitive load? What is this intent-first focus really about?
It's the move from tactical implementation to strategic definition. In the traditional way of working, your mental energy was just. It was
Yeah.
exhausted dealing with syntax errors, managing dependencies, writing all that routine boilerplate.
The daily grind.
Exactly. In the AI era focus, your true value, your real worth, is derived from your ability to define the problem. The desired outcomes, the non-functional requirements like latency and scalability, the system specifications, and to do it all with precision and clarity.
So the value isn't key process anymore.
Not at all. The human judgment, the strategic system design, the overall vision, those are the real value drivers now. If a task can be solved by simple coding, it will soon be fully automated. So the distinction between a good engineer and an elite engineer is now defined by their ability to make strategic architectural decisions and design what should be built, not just how to build it perfectly.
This shift towards defining intent brings us to a phrase that sounds, I have to say, delightfully informal, but it actually represents a really rigorous emerging skill: vibe coding.
I know, the name is a bit funny.
What does vibe coding actually mean in a serious engineering context?
Vibe coding is the skill of getting high-level, complex, and correct results from an AI by using these well-crafted, concise natural language specifications. It's, in a way, the new form of declarative programming.
So instead of telling it the steps, you're telling it the end state.
Precisely. You're not saying, write a function that iterates through this array and does X, Y, and Z. Instead, you define the intent and the constraints. Something more like, generate a reusable React component that displays customer sales data in a sort of table. It has to adhere to our material UI library. And oh, make sure it's AAA compliant for accessibility.
It sounds like the engineer is now designing a new kind of API, one that speaks directly to the large language model.
That is a perfect way to put it. It's a language-based API between the engineer and the machine. And this concept is so fundamental, it's actually being formalized in academia as the vision for the next stage of the discipline.
And what are they calling it?
Researchers are calling it Software Engineering 3.0.
SE 3.0.
Yeah.
That sounds like a formal declaration that the era of manual coding is, I don't know, coming to an end.
It is exactly that. SE 3.0 is fundamentally focused on three things: intent, conversation, and co-decision-making. It signifies the formal end of manual code translation as the core skill.
So what does that process look like now?
The process is no longer a human manually translating a requirement into 1,000 lines of code. It's a conversation. The human defines the requirement, the constraints, the architecture, and the AI handles the translation, the iteration, and all the implementation details. This just acknowledges that complexity has moved up the stack from syntax to orchestration.
And if the engineer is guiding the AI through conversation, they become the orchestrator. How does the mindset of an orchestrator differ from, say, a traditional senior engineer who is primarily focused on execution and delivery?
The orchestrator's primary focus is quality control and strategic oversight. The elite engineer acts as the approving authority, not the generator.
So you're the editor, not the writer.
A very, very senior editor. You are guiding a powerful, eager, but often unreliable junior partner. The key differentiator is understanding that AI-generated code is probabilistic. It's high velocity, but it has variable quality.
Which means you need rigorous review.
It requires rigorous human-in-the-loop review. We're not just accepting the AI's output blindly. We are reviewing it with senior-level skepticism. We're asking, did it miss an edge case? Is this secure against prompt injection? Does it align with our cost and latency requirements? This mentality shifts the burden from typing fast to critically analyzing, debugging, and maintaining control.
But wait, if the AI is providing these 30 to 50% velocity gains, why are we designing systems that require more focused, senior-level manual review? Isn't the whole goal to eliminate that friction?
That's a great challenge, and it really hits on the core trade-off. We're trading quantity of review for quality of review. An engineer used to spend time reviewing basic syntax and structure. Now, they spend that same time reviewing architectural soundness and security vulnerabilities, which are much higher value tasks. So the friction is reduced on the mechanical side, the typing and boilerplate, but it's concentrated on the strategic side, verification and security.
So the real elite engineer finds a way to automate the verification too.
That's the end game. You integrate the verification into the AI system itself, and that's where flow engineering comes in. You build the guardrails right into the workflow so the human is only really needed for the highest risk decisions.
That transitions us perfectly.
Yeah.
We've established that clear language is the new currency. But for complex tasks, the sources suggest that what we've been calling prompt engineering, crafting that single perfect input, is already not enough.
It's already becoming obsolete for complex work.
Why? Why is simple prompting failing at scale for modern engineering challenges?
Simple prompt engineering is effectively System 1 thinking. It's fast, it's intuitive, and it's great for isolated low-stakes tasks, like generating a quick function or summarizing a short document.
But not for building a whole feature.
No. When you apply it to complex, multi-step engineering challenges, like fixing a cross-module bug or refactoring a legacy service or conducting deep technical research, it becomes brittle. It breaks.
And why is that? What's the technical limitation?
It's because a single monolithic prompt is constrained by the LLM's single inference pass. It has no memory of steps, it can't easily self-correct, and its reasoning chain is totally opaque. You are basically asking the model to produce a perfect soufflé on the first try without any quality checks at the intermediate stages.
Which leads to
A much higher rate of factual errors, logical inconsistencies, and hallucinations. Especially when you're dealing with long horizon problems, it just doesn't scale to the complexity of enterprise software.
So the solution is to move to System 2 thinking, which you mentioned is flow engineering. Can you define flow engineering for us and explain how it really revolutionizes the way we structure these interactions with LLMs?
Absolutely. Flow engineering is the mastering of a multi-step, deliberative, and structured logical process. Instead of asking one large, complex question, you construct an architectural flow. It's a sequence of smaller, verifiable steps.
A chain of commands.
A chain of verifiable commands where the output of one LLM interaction is validated, transformed, or used as precise, constrained context for the next step.
So you're breaking the problem down.
Exactly. Think of it less like writing a letter, which is a single prompt, and more like designing a factory assembly line, which is a flow. Each station on that line performs a single, specialized, verifiable task before passing the result to the next station. This gives you, the engineer, maximum control, transparency, and most importantly, debugability.
That makes perfect sense. You're applying traditional software architecture principles, modularity, separation of concerns, to the LLM interaction itself. So if we're using this flow, where does the control actually move?
The shift is fundamental, and this is something every elite engineer needs to internalize. The locus of control moves away from the quality of the prose, the cleverness or the detail of the individual prompt, to the quality of the architecture, the flow itself.
So it's not about being a good writer, it's about being a good architect.
You are designing the overarching logic, the specific sequence of steps, the required inputs at each stage, the decision points. You stop relying on the LLM to magically execute a massive monolithic request perfectly. Instead, you dictate the structure, and the LLM becomes a high-speed inference engine executing a highly specialized function at each step of your design.
That sounds like it adds some overhead, though. For the average engineer who's just trying to build a small service this week, how much overhead does flow engineering really add compared to a simple prompt, and is it worth it?
It definitely adds upfront design overhead, there's no question, but it drastically reduces the debugging and verification overhead later on.
The trade-off again.
It's always a trade-off. If you're solving a trivial problem, sure, use a simple prompt. But if you're solving a complex problem that involves multiple files, or external data retrieval, or nuanced constraints, say, generating a secure OFU flow component, then flow engineering is essential.
Can you give us a concrete example? Contrast the two approaches for a mid-level task.
Yeah, let's take a common task. Analyzing some existing code before a major refactor. With simple prompting, you might ask. Analyze the database interaction module, find the performance bottlenecks, and suggest a refactored solution.
Then you get a wall of text back.
You get one long synthesized answer, and now you have to spend an hour verifying every single line, trying to figure out what's real and what's a hallucination.
Okay, now the flow engineering approach.
With flow engineering, you architect the process. So, step 1, you have an agent, let's call it the scanner. Its only job is to read the module and generate a structured list of all the database queries, a constrained output.
Right.
Step 2, Agent 2, the critic. It takes the scanner's list and runs a static analysis tool against those queries, flagging any missing indices or N+1 issues. That's a validation step.
So it's checking the work.
It's checking the work. Step 3, Agent 3, the strategist. It only takes the flagged issues and the original code, and only then does it generate the specific refactoring plan and the new code snippets.
And it doesn't proceed until the critic is happy.
Exactly. And then you can have a step 4, an agent 4, the verifier, which generates new unit tests specifically targeting the performance improvements. The flow enforces rigor. This architectural approach ensures robustness and reliability, and it makes the output so much safer and vastly reduces your manual review time.
That structured iteration is clearly the key to reliability. And flow engineering seems to rely heavily on another specialized skill mentioned in the sources. Context engineering. What does that discipline encompass?
Context engineering is the indispensable complementary discipline. It focuses on curating the optimal set of tokens, the precise information that you provide to the AI during inference.
It's not just what you ask, but what information you give it.
Precisely. As LLMs get these exponentially larger context windows, the challenge has flipped. The issue is no longer how to ask, but what information to provide and when to guide the model successfully. The goal is to provide just enough highly relevant data to prevent hallucinations without overwhelming the token limit, confusing the model, or, incurring massive operational costs.
So what are the specific strategies elite engineers are using in context engineering to manage that balance between relevance and cost?
There are 2 main strategies that every elite AI native engineer really needs to master. The first is compaction. This involves techniques to summarize or condense prior conversational history, large documents, or previous steps in the flow just to maintain continuity without exhausting the token limit. For example, in a long debugging session, you don't feed the entire chat history back to the model.
That would be incredibly expensive and slow.
And confusing. Instead, you feed back a high-quality summary of the steps taken so far and the current, most relevant error state. You keep the context rich, but syntactically succinct.
Okay, so that's compaction. What's the second strategy?
The second is JIT context, which stands for just-in-time context. It's commonly implemented through retrieval augmented generation, or RA.
We hear a lot about RAG.
You do. And you can think of JIT context as hiring a highly specialized librarian for your AI. Instead of giving the AI a general prompt and just hoping it remembers your complex internal project standards.
Which it won't.
It won't. The engineer designed the flow to retrieve relevant documentation or specific configuration files or internal data only when the flow specifically requires it. And then you inject that context into the prompt immediately before the generation step. By providing that highly targeted project-specific context right at the point of decision, you drastically reduce hallucinations and improve accuracy. It's critical when the task involves internal project knowledge that the general model couldn't possibly know.
So flow engineering gives us the structure, but the cutting edge is moving toward full autonomy, which brings us to agentic workflows. Let's clarify the distinction here, because this is where the terminology can get tricky. What fundamentally distinguishes an agent from a standard workflow?
This distinction is non-negotiable for anyone who's building the next generation of software. A standard workflow, like we defined, is linear and predefined. It's A, then B, then C. It just executes a static plan.
Right.
An agent, however, is distinguished by 2 core characteristics: autonomy and the capacity for reasoning.
So it thinks for itself.
In a way, yes. An agent has the ability to evaluate the current state, reflect on its goal, and then dynamically decide its next step. It's an intelligent entity that uses internal logic to determine if it should proceed to step B, or maybe branch to C, or perhaps loop back to A to collect more data. It's goal-oriented. It has agency to pursue that target dynamically rather than just executing a static script.
So the agent plans and decides based on observation, while the workflow just executes a predetermined sequence. The sources highlight something called the react pattern as the foundational loop for this. Tell us how that cycle works.
The react pattern, which stands for reason plus act, is the minimum viable architecture for true agentic behavior. It's an alternating, self-correcting loop that really mimics the scientific method.
Yeah.
The agent alternates between reasoning, which is like an internal monologue about the current state, the goal, and the strategy, and acting, which is executing a tool or a function in the external environment. Then it refines its approach based on the observations returned by those actions, and it just repeats that loop until the goal is met or it fails.
Let's make that more tangible. We had a brief example before, but can you walk us through a more detailed coding example of an agent fixing a subtle bug using that React loop?
Yeah, of course. Let's say the goal is fix the intermittent user session expiration bug in the main API gateway.
A classic annoying bug.
A classic. So step 1, the initial state observation. The agent reads the user's bug report, which includes a cryptic traceback, and mentions it only seems to happen on mobile devices.
Okay.
Step 2, reasoning 1. internal monologue. The agent thinks, okay, the error suggests a state issue on refresh. I need more context about the request setters, specifically the user agent data, which is only logged in the verbose stream. My goal is to reproduce this issue.
So it forms a hypothesis.
Exactly. Step 3, Act 1, tool use. The agent uses a lockery tool to search the verbose logs for mobile user agents associated with that error over the last 24 hours.
It gathers data.
Step 4, Observation 2. The logs come back and confirm that the mobile browser is sending an unexpected, malformed cookie header during the session refresh attempt.
Ah, the smoking gun.
There it is. Step 5, Reasoning 2. The agent thinks the malformed header is the cause. I need to implement a sanitization step before the session check. I will first draft the necessary rejects and a new unit test to cover this specific edge case.
It plans the fix.
It does. Step 6, Act 2, tool use. The agent uses its code interpreter tool to generate and apply the sanitization logic within the correct file, say session_middleware.py, and at the same time it generates the new unit test.
And then it tests its own work.
Step 7, Observation 3. It runs the test suite, and the new test fails. The fix wasn't perfect.
So it self-corrects.
This is the key part. Step 8, Reasoning 3, Reflection. It reflects the sanitization logic was too aggressive and it removed a necessary token. I need to loosen the rejects to preserve the xClient ID token while still scrubbing the malformed part. I will try again. And then it goes back to Act 3, and so on. That ability to dynamically reflect, adjust the plan, and use tools based on observation is what makes it a true agent.
That detailed reflection loop really highlights the difference. But for engineers to trust these agents with potentially system-critical changes, reliability is everything. What are the core agent design patterns being used in production to enforce that rigor and, mimic human QA processes?
Right, this is crucial. We see organizations codifying 3 primary design patterns, all aimed at making agents predictable and rigorous. The first is the reflection pattern.
Which we just saw in action.
Exactly. It's maybe the most crucial one for reliability. The agent doesn't just execute. It assesses its own results before declaring success. The standard implementation involves defining a primary coder agent that generates the solution, and then a separate critic agent.
A built-in code reviewer.
Yes. A built-in automated code reviewer. The critic agent reviews the output based on a defined set of criteria, security, complexity score, adherence to your project rules. And the critic will actually force iteration. It rejects the output and sends it back to the coder until it's satisfied. This is vital in preventing what's called the illusion of competence, where the AI generates plausible but flawed code. You build skepticism right into the architecture.
Okay, so that's reflection. What's the second pattern?
Second is the planning pattern. This is where agents decompose complex goals into a sequence of smaller, manageable subtasks. So if you ask it to build a secure data ingestion pipeline, it doesn't try to do it all at once.
That breaks it down.
It reasons first. Step 1, define the schema. Step 2, implement the authorization layer. Step 3, write the ETL logic. This chain of thought reasoning ensures the agent approaches the problem logically and tackles dependencies sequentially.
And the third pattern?
The third is the tool use pattern. This is how agents expand their capabilities and ground their logic in reality by interacting with external environments. They use tools, which are just wrappers around non-LLM functions, web browsers for real-time info, APIs for system interaction, code interpreters for execution. For example, an agent tasked with verifying deployment status will use a kubectl or Terraform tool rather than just hallucinating the status. This is what expands the agent's scope beyond pure language generation into the operational realm.
So if an engineer wants to move beyond simple scripting and start building these multi-step agentic systems today, what frameworks should they be looking at? Our sources point to a sort of philosophical contrast between 2 big ones, LangGraph and DSPy.
They do. And these 2 frameworks really represent the 2 dominant philosophies of agentic control. Understanding the difference is key to choosing the right tool for the job.
Let's start with LangGraph.
Okay, so LangGraph is the graph-based orchestrator. It's built on the established LangChain ecosystem, but it specializes in adding cyclic capabilities, loops, and rigorous state management. You can think of LangGraph as the expert in system wiring.
The plumbing?
The plumbing. It models agents, tools, and human review steps as nodes in a graph. This allows you to visually or programmatically define these complex, stateful branching workflows. And it's highly effective for scenarios where you absolutely need the human engineer in the loop,
How so?
because you can define a state transition that requires human approval before the agent is allowed to, say, commit code or deploy a service or move to the next high-risk state. It gives the engineer very granular control over the agent's entire journey.
Okay, so that's LangGraph. What about the other one, DSPy?
DSPy, which stands for Declarative Self-Improving Language Programs, is, by contrast, the declarative optimizer. This represents a more radical approach. Instead of you manually designing the flow, the wiring, the developer defines the high-level logic and the success metric.
What a good outcome looks like.
Exactly. For example, maximize query accuracy to 95%. DSPy then automatically compiles and optimizes the hidden internal prompts used in the agents to maximize that success metric using its own self-reflection. Think of DSPy as the engine tuning expert.
So it figures out the best prompts on its own.
It does, and it abstracts away the extreme fragility of manual prompt engineering. The massive advantage here is adaptability. If the underlying LLM model, say GPT-4, changes, DSPy can automatically recompile or re-optimize the internal prompt structure to suit the new model's behavior, all without human intervention. It ensures your reasoning stays reliable.
So just to summarize, if I need granular control over the exact sequence and I want human approval points, I use LangGraph, the wiring.
Right.
But if I'm building a system where the performance metric is the sole focus and I just want the best possible output, I choose DSPy, the engine tuning.
That's a perfect summary of the distinction. One is about managing state and sequence. The other is about maximizing reasoning quality and efficiency. An elite engineer needs to know both.
The need for reliability brings us back to rigor. We've talked about agents and flows, but we have to acknowledge their output is still inherently probabilistic. And the sources argue that we have to abandon our traditional deterministic approach to testing in favor of something entirely new, evils-driven development, or EDD. Why is EDD so necessary in this new world?
The necessity of evils, it all stems from recognizing the core philosophical difference between traditional software and AI systems. In traditional software, if you input X, you expect output Y every single time. 2 plus 2 always equals 4.
Deterministic.
Exactly. In the world of LLMs and agents, 2 plus 2 usually equals 4. But if the model temperature is high, or the context is ambiguous, or the internal state is just slightly off, it might return 5. And it might do so very confidently.
Right.
We have to accept that system behavior is a distribution, not a constant. And because of that, we can't use simple unit tests that assert a single specific expected output. EDD is the adoption of the scientific method testing hypotheses and measuring behavior across a broad statistical range applied directly to our LLM systems.
So how does EDD work in practice? I mean, how do you measure the quality of a creative language-based output?
EDD revolves around defining a rigorous golden data set. This is a set of representative inputs and their meticulously defined ideal expected outputs. You then run your entire AI system, your prompt, your flow, your agent, against this golden data set repeatedly.
And the output isn't just pass-fail.
No, the outcome is a quantifiable score. You measure metrics like correctness, helpfulness, coherence, or accuracy relative to that ground truth. And since assessing text quality is so subjective, EDD frequently uses a key innovation, using a stronger, more capable LLM like GPT-4 or Claude as the judge.
So you use an AI to grade the AI.
You do. This judge LLM is provided the input, the expected output from your golden set, and the actual output from the system you're testing. The judge then scores your system's output based on a detailed set of criteria you give it, like, did the output adhere to security constraints? Score 1 to 5. This transforms prompt engineering from an intuitive art into a quantifiable empirical science. You can prove, statistically, that flow A is 12% more reliable than flow B.
That structure of develop, evaluate, and iterate, it sounds like it creates a continuous improvement cycle. The sources call it the AI native flywheel.
Exactly. EDD enables this continuous self-optimizing cycle. You develop a prompt or a RAG strategy or an agent flow. You evaluate it using the judge and the golden data set to get a score. You log the results, tracking latency, cost, reliability, and then you iterate, tweaking the architecture of the prompts and instantly rerunning the evaluation suite.
So you have hard data to guide your improvements.
You have empirical data on which architectures, which context strategies, which prompts actually perform the best. It's absolutely crucial for complex agentic RG systems where retrieval accuracy is the single greatest point of failure and has to be rigorously tested.
Moving from the abstract rigor of EDD to the daily work environment, the engineer's workbench itself is changing. We're seeing a shift from simple text editors to these AI-native IDEs, with tools like Cursor being cited as a leading example. What makes these new IDEs a necessity rather than just a luxury?
AI native IDEs fundamentally change the physics of a developer's day. They integrate AI directly into every core editing action, moving way beyond simple autocomplete. Tools like Cursor enable what you could call tab coding, where the AI predicts the next full logical code block, the next function, or even the next file you need to open.
And what about editing existing code?
That's where Command K editing comes in. You can modify large blocks of code using natural language instructions. This just dramatically lowers the cognitive load for all the mechanical tasks, shifting your focus to high-level intention.
The sources specifically highlight a critical innovation in these IDEs, the .cursor rules file. For an elite engineer, why is this file such a game changer?
The .cursor rules file is arguably one of the most important new file types in an AI native repository. It's a game changer because it allows you to codify project conventions, context, and stylistic best practices directly into the repository right alongside the code itself.
So it's not just in a wiki page somewhere that nobody reads.
Exactly. Historically, this information was trapped in documentation or tribal knowledge or just endless human code review comments. Now, you can write explicit machine-readable rules that instruct the AI assistant.
Like what kind of rules?
Well, you could have an architectural rule like always use the repository pattern for database access, never inline SQL, or a stylistic one. Prefer functional components in React and always use TypeScript interfaces for props. Or even a security rule. All user inputs must be validated with the Zod library before processing.
And this ensures that the AI's output is consistent with your project standards from the start.
Before it's even submitted, it radically improves consistency and just slashes the time human code reviewers spend on style and minor refactors.
And these IDEs also integrate the concept of autonomy via an agent mode. How does that amplify an engineer's capability beyond just writing a function faster?
Agent mode is where the IDE truly becomes an AI partner, not just a suggestion tool. It allows you to prompt the IDE to autonomously perform large-scale, cross-file mechanical tasks that used to take hours or even days of painstaking work.
So a big refactoring task, for example.
A perfect example. Imagine you're tasked with updating a system to handle a new version of a framework. You can just prompt it. Find all calls to the deprecated API X across the services directory and rewrite them using the new API Y. Make sure all necessary imports are updated and check everything against our .cursor rules file.
And the agent just goes and does it.
It traverses hundreds of files, makes the changes, fixes dependencies, verifies compliance. This frees you, the human, from all that mechanical cognitive load, allowing you to focus entirely on the high-level architecture and verification. The only caveat, of course, is that this power demands you provide clear context. Garbage in, garbage out still applies.
So we've established that AI automates the mechanical parts of the job, and the tools are becoming more intelligent. So what defines the essential, irreplaceable human value in this new paradigm? The sources suggest the rise of the product engineer. What does this newly empowered role truly emphasize?
The product engineer signifies the formal blurring of traditional technical silos. Front-end, back-end, infrastructure, and now, increasingly, product management. This role is defined by owning the outcome, the user value, the business metrics, the holistic delivery, rather than just the implementation.
Not just the code in one repository.
Not at all. And AI enables this role because an engineer can now traverse the full stack with incredible speed. A front-end specialist can use an AI agent to quickly generate the necessary database migration, or the specific SQL query, or a new API endpoint template. This allows them to deliver a feature end-to-end without being blocked or needing deep expertise in every single layer.
So the mindset shifts from code ownership to value ownership.
Perfectly said. It's a psychological shift across the entire delivery spectrum.
So if AI can write the routine code, what are the skills that remain exclusively in the human domain? Which ones become the highest value drivers for an elite engineer?
These are the skills that rely on tacit knowledge, strategic context, and complex emotional intelligence, things AI still profoundly struggles with. The sources consistently identify what's called the multi-spired model, suggesting engineers need to deepen their expertise in 3 irreplaceable areas.
Okay, what's the first one?
First, strategic judgment. This is the ability to design what should be built, and critically, what should not be built. It involves making those high-level trade-offs, balancing technical debt against short-term revenue goals, optimizing cloud cost versus performance, assessing organizational risk.
The things a manager worries about.
Exactly. AI can present options, but only the human with that political and business context can make the strategic decision. This requires deep domain literacy and risk assessment
Okay,
skills.
that's judgment. What's number two?
Second, communication and empathy. AI cannot lead a complex stakeholder meeting. It can't navigate organizational politics, gather ambiguous requirements from a non-technical client, manage expectations, or mentor a junior team member through a crisis. Interpersonal skills, collaboration, conflict resolution, these are core human differentiators that will only grow in value.
And the third.
Third is mastery of system design and architecture. While AI can write a single class or a microservice, architecting large, complex distributed systems, ensuring fault tolerance across dozens of services, designing asynchronous communication patterns, mastering database sharding, predicting failure modes at planetary scale, that remains distinctly human. It's an architectural art form that AI does not yet possess.
Let's turn to a major sociological consequence noted in the sources, which is the crisis of the junior developer. This seems like a real talent paradox in the making.
It absolutely is. And managers need to be hyper aware of this. Historically, junior developers earn their technical literacy and domain knowledge by doing the grunt work.
Writing the unit tests, fixing simple bugs.
Right. Building small, self-contained features. This repetition allowed them to build a mental map of the system and acquire syntactic fluency. But today, AI automates this exact grunt work faster, cheaper, and often with higher quality boilerplate.
Creating what the sources call the apprentice paradox.
The apprentice paradox. If AI automates the very tasks designed to train and socialize juniors, how do they acquire the architectural literacy and deep code intuition they need to become seniors? The industry risks collapsing the entire talent pipeline if we don't adapt.
So the grunt work is gone. What does the new entry-level role even look like? And what do managers need to change?
The entry-level role is rapidly shifting from the writer of code to the reviewer of AI code. Instead of learning to generate code, juniors must now be explicitly trained to review, debug, verify, and spot subtle AI hallucinations or security flaws in code that they did not write.
But that's a senior skill.
Paradoxically, yes. It requires deep critical thinking, strong security literacy, and architectural awareness skills that have traditionally been reserved for senior-level expertise. Managers have to recognize this skills gap. They need to create explicit, systemized training programs focusing heavily on architectural patterns, flow engineering design, and system debugging, using AI-generated code as the subject for critique, not the final product. We have to train critical thinking, not just typing speed.
The risks aren't just managerial, they're cognitive. The sources mention the sociological risk of cognitive atrophy. How does relying on AI synthesis affect the human mind? And how do we guard against it?
This is a profound concern, and there's initial research suggesting it's a valid worry. We all know the feeling. If you rely on a calculator for complex arithmetic for too long, simple sums start to feel taxing. That's cognitive atrophy in action.
Your mental muscles get weaker?
They do. Excessive reliance on AI synthesis, where the machine does the heavy lifting of structuring arguments or generating complex code, may lead to a reduction in critical thinking, problem decomposition, and deep retention. If the AI just gives you the answer immediately, your brain may bypass the complex processing required for true understanding.
So for the elite engineer, what's the rule?
The rule has to be, guard the bedrunner skills. You must actively guard against becoming a passive consumer of AI output. You have to actively engage, challenge the AI's assumptions, force yourself to debug its internal reasoning, manually verify its sources. Sometimes you have to force yourself to decompose and synthesize complex ideas by hand. It's about maintaining the mental fitness required for strategic decision-making. Treat the AI as a brilliant but untrustworthy colleague that you have to constantly scrutinize.
And finally, on risks, as agents gain more access and autonomy, what new security risks are we introducing?
As autonomous agents are granted identity within our digital systems, meaning they have privileges to read databases, commit code, interact with internal APIs, they create an entirely new, massive attack surface. The primary risk is prompt injection.
How does that work?
Attackers can manipulate an agent's input instructions, often through subtle data hidden in external files or retrieved context, and force it to exfiltrate proprietary data, perform unauthorized actions, or bypass security checks.
And there's a more advanced threat too, right?
Yes, vibe hacking. This targets the probabilistic nature of the model itself. An attacker might manipulate the tone, or the confidence score, or the implicit context of a prompt to trick the agent into lowering its guard or behaving unreliably. For example, structuring an input that the agent registers as an urgent crisis might cause it to skip its standard security verification step.
What's the defense?
The defense mechanism for 2025 and 2026 shifts heavily toward identity-centric defenses. We have to treat AI agents as highly privileged users and enforce strict least privilege access controls on all of them, monitoring their actions with the same scrutiny we'd apply to a human sysadmin.
This has been an essential breakdown of the new landscape. It all points toward a required, high-stakes strategic action plan. We've gathered a structured, phased roadmap for you, the listener, starting with the necessary commitment, continuous learning.
That commitment is non-negotiable. Adaptability, not static knowledge, is the ultimate competitive edge. The foundation of this blueprint requires a dedicated, structured learning habit. Our sources consistently suggest that elite performers schedule about 15% of their time weekly, that's roughly 6 hours, for proactive learning.
What should you be doing in that time?
Experimenting with new tools, diving into new research papers, exploring emerging paradigms like flow engineering and SE 3.0, you have to be proactive and experiment early. Waiting for your company to provide training is waiting to fall behind.
Let's walk through the 3 phases of the Elite Engineer Blueprint, starting with the immediate foundational action plan for the first 3 months.
Okay, phase 1, build foundation and fluency, first 3 months. The core objective here is to move from passive awareness to daily demonstrable competence and high velocity.
Action 1.
Action 1, master AI fundamentals. You don't need to be an ML researcher, but you need to understand the mechanics enough to debug failure. Focus on how transformer models work, the limitations of the context window, the difference between supervised and unsupervised learning, and the conditions under which hallucinations occur. Understanding the mechanics helps you design effective flows and anticipate failure.
Okay, action 2.
Action 2, daily hands-on tool fluency and prompt library creation. Commit to using an AI coding assistant for every mechanical coding task. And crucially, start logging your successful prompts. Don't just save the code, save the prompt that produced the best code. Build your personal codified prompt library for tasks like generate a secure endpoint schema. You should be aiming for a verifiable 30–40% reduction in time spent on repetitive tasks.
And the third action for this phase.
Action 3, double down on system design literacy. Since the AI handles the code, the human must handle the architecture. Use those 15% learning hours to refresh or deepen your knowledge of complex system design topics, scalability, microservices, communication patterns, distributed systems theory, high availability.
Okay, so once that fluency is established, we move into the strategic phase, which extends up to 9 months. What is the goal of phase 2?
Phase 2, strategic expertise, 3 to 9 months. This phase is all about applying AI to increase your strategic impact beyond mere code generation, focusing on quality and architectural leadership.
What's the first action here?
Action 1, integrate AI into the SDLC. Move AI tools from personal use to team-wide automation. Start using AI tools in your CI/CD pipelines for automated code quality checks, security scanning, and automated documentation generation. Your goal should be to lead the creation of a team-wide playbook on AI collaboration that demonstrably improves PR quality and accelerates velocity.
And after integrating, what's next?
Action 2, embrace flow engineering mastery. Build and deploy your first agentic workflow using a framework like LangGraph or DSPy. Start small. Automate the triage of incoming support tickets, or build a simple RG system that answers common questions about your internal code base. Focus on designing the flow architecture and implementing those evals we talked about.
And the final action for phase 2.
Action 3, focus on business collaboration and design thinking. Leverage the time you've saved by AI to attend product meetings and deeply understand user stories. Use AI to analyze initial requirements to uncover hidden complexities and de-risk the project up front. Use it to quickly mock up 3 different architectural solutions for your team to discuss. Your goal is to be recognized as the engineer who bridges the gap between the technical and the business needs.
And what does the long-term view, year 1 and beyond, look like for specialization and leadership? This marks the true transition to the elite engineer.
Phase 3, specialization and leadership, year 1 and beyond. This is the strategic transition to organizational influence. You have to target the high-value, high-complexity areas where AI struggles or where its integration is inherently hard. That's what makes you indispensable.
And what are those specialization areas?
There are a few key ones. AI security and ethics, focusing on defending against prompt injection. MLOps and reliability engineering, mastering the deployment and monitoring of these systems. AI integration architecture, becoming the expert in how humans, legacy systems, and agents interact. And a huge one, legacy system modernization, using AI to analyze and refactor massive, decades-old code bases.
And on the leadership side,
You transition from managing code to managing systems and people. Mentor junior colleagues on these new critical thinking skills. Lead cross-functional initiatives. Publish your technical insights, internal talks, white papers that establish you as a thought leader who shapes the engineering direction for your whole organization.
that is a comprehensive and structured roadmap. Speaking of high impact, the sources provided some truly career-defining project ideas for you to tackle projects that instantly demonstrate that staff or principal level scope. What are some of these critical needle-moving projects?
These are projects that directly solve complex organization-wide pain points related to AI reliability and velocity. One highly valuable project is building an AI-assisted code review system.
More than just a linter.
Much more. This service would analyze pull requests using multiple specialized AI agents to flag security risks, performance risks, and logic risks. And crucially, it has to explain why the code is risky and learn your specific team standards from that .cursor rules file. This scales quality across the entire engineering department.
It's another one.
Another essential project is developing an AI reliability and guardrails framework. This targets the probabilistic nature of AI head-on. This framework has to detect hallucinations in agent output, apply confidence scoring to critical decisions, implement fallbacks for when confidence is low, and ensure detailed audit logging for every autonomous decision. Very few engineers can build this well, making it an immediate marker of elite expertise.
And a final idea.
A final high-impact idea is creating an AI-enhanced internal developer platform, IDP. This leverages vector databases and LLM APIs to ingest your organization's entire code repository, all the internal documentation, even meeting notes. It would allow any engineer to query the codebase via chat to understand system logic like how does service X communicate with database Y and generate onboarding documentation. It has a direct, quantifiable business impact by reducing new engineer ramp-up time from months to weeks.
These projects clearly define the scope of the elite engineer.
Yeah.
Someone focused on scaling intelligence, not just code. This all culminates in the final distinction, the elite mental model. What is the final shift in thinking we need to internalize?
The change is subtle, but it's what profoundly separates the top tier. You have to completely eliminate the old mindset, which focused on competing with the machine on speed, and fully adopt that orchestration mentality.
So what's the old thought versus the new thought?
The senior engineer of the past thought, I write better code than AI, the elite engineer thinks. I design robust, verifiable systems that AI cannot reason about alone.
And what about speed?
They don't think. AI helps me code faster, they think. AI multiplies my architectural, strategic, and leadership impact across the entire organization. The ultimate goal is that strategic transition from an implementation-focused senior engineer to a recognized AI-enhanced architect, strategist, and technical leader. That's what guarantees your relevance.
That roadmap is incredibly detailed and actionable. If we were to synthesize the single most important key takeaway from this deep dive, from mindset to tools to career path, it is that the competitive edge in the AI era is defined not by typing speed,
Not at all.
but by strategic judgment, architectural systems thinking, and leadership capacity.
Absolutely. The future firmly favors those who orchestrate and design intelligence rather than those who try to compete with it on raw output. By mastering the structure of flow engineering, adopting agentic workflows with rigor, and committing to the quantifiable science of evils-driven development, you are positioning yourself as much more than a coder. You're positioning yourself as an architect of intelligence, the person who designs the intelligence layer of the system itself.
A compelling note to end this deep dive on. Now for our final provocative thought for you to mull over. The sources predict that the vibe, the initial hype surrounding AI integration, will inevitably give way to measurable return on investment and accountability by 2026. The question you should be asking yourself is not simply whether you are using AI tools, but how you are quantifying the reliability, the maintainability, and most importantly, the tangible business value of the new intelligence systems you are designing around them. The measurable value is the only thing that will sustain and reward this profound shift.